Hello student, welcome to my third lecture on chapter number 4, that is atomic structure. In this lecture we have to discuss about what is the development leading to the Bose atomic model. At the time when different models of atomic structure were being put forth, some result obtained from the studied of interaction of radiation with matter required to correlated to atomic structure. Niels Bohr utilized these results to give over the drawbacks of Rutherford atomic model. These results were first one, that is wave particles duality of electromagnetic radiation, and second one, that is line emission spectra of hydrogen. Now you have to discuss what is the first one, wave particles duality of electromagnetic radiation. A dilemma was proposed by electromagnetic radiation in the world of science. Phenomena such as diffraction and interference of light could be explained by treating light as an electromagnetic wave. And second one, on the other hand, the blackbody radiation of or photoelectric effect could not be explained by wave nature of light and only recorded by considering particles nature of light. Okay, next continues this duality of electromagnetic radiation. The only way to resolve the dilemma was to accept that light has dual behavior. First, when light interacts with matter, it behaves as a stream of the particle called photon. When light propagates, it behaves as a electromagnetic wave. That's simply how to show the figure. In this figure, first figure, these electromagnetic and magnetic and electric both fields are there, both are perpendicular to each other, and at that time this light, simple light will be propagate. At that time it shows the wave nature, and light will be interact with matter, it shows the stream of particle, that is photon. Okay, now some characteristic of electromagnetic wave are discussing here, that is the above figure shows a schematic representation of an electromagnetic wave, whereas parameters used to describe the different types of electromagnetic radiation are wavelength, frequency, wave number, amplitude, and velocity. These are discussed below. First one, wavelength. The distance between two consecutive crests or toes is called wavelength. It is represented by symbol lambda, which is Greek letter, and is generally expressed in the terms of angstrom unit, denoted by A node. 1 angstrom is equal to, we know that is 10 raised to minus 8 centimeter or 10 raised to minus 10 meter. It can also be expressed as micrometer, micron or micron meter, millimicron meter or nanometer and picometer, etc. These units are related to SI unit meters as 1 angstrom is equal to 10 raised to minus 10 meter, 1 millimicrons is equal to 10 raised to minus 3 meter, 1 micron is equal to 10 raised to 6 meter, 10 raised to minus 6 meter, and 1 nanometer is equal to 10 raised to minus 9 meter. Lastly, 1 picometer is equal to 10 raised to minus 12 meter. Okay. Next one. Second characteristic, that is frequency. The number of waves that pass through a given point in 1 second is called frequency. It is denoted by Greek letter nu. The unit of frequency are cycle per second or simply reciprocal of seconds. The SI unit of frequency is hertz, that is Hz s minus 1 after the name of Heinrich Hertz. 1 hertz is equal to 1 cycle per second. A cycle is said to be complete when a wave considering of crest and toes pass through a point. Simply you have to remember is 1 cycle is when complete, 1 crest and 1 toes will be completely converted, joined to the given point. Third point, that is wave number. Wave number is the number of wavelength per unit length. Wave number is represented by the symbol nu bar. The commonly used unit for wave number is reciprocal to centimeter, that is C minus 1. While the SI unit is meter inverse. Wave number is related to the wavelength by an expression nu bar is equal to 1 upon lambda. Okay. Next, amplitude. Amplitude of a wave is the height of crest or depth of toe of waves. This is what is the crest and what is the toes. This concept you have to simply observe in figure. Square of the amplitude denote the intensity of radiation. Different region of electromagnetic radiation have different values of frequency or wavelength. Thus, the ratio of frequency region is around 10 raised to 16 Hz. Microwave region is around 10 raised to 10 Hz. IR region is around 10 raised to 13 hertz and UV region is around 10 raised to 16 hertz. In vacuum, the speed of all the type of electromagnetic radiation is the same, which is 3.0 into 10 raised to 8 meter per second, or the value of this in bracket 2.997925 into 10 raised to 8 meter per second to be precise. This simple, this value are important, you have to rememberize. This is called speed of light or velocity of light and is denoted by C, letter C. The parameter wavelength, frequency and velocity are related by the expression C is equal to lambda into nu, lambda into nu. Then if you calculate nu, then that is equal to C upon lambda, or 1 upon lambda is equal to nu bar. Then nu bar is equal to nu is equal to, you have to simply write C into nu bar. Okay. Next, that is second point, particle nature of electromagnetic radiation. In the year 19th century, Max Planck forth his quantum theory to explain blackbody radiation. According to this theory, the energy of electromagnetic radiation depend upon the frequency and not on the amplitude. Planck gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy E of the quantum of radiation is proportional to its frequency and given by E is equal to h nu. The proportionality constant h is called Planck's constant. Later, its value was found out to be 6.626 into 10 raised to minus 34 joule per second. In the year 1905, Albert Einstein explained the photoelectric effect using Planck quantum theory. In doing so, he considered electromagnetic radiation as a stream of photons of energy h nu. A photon has zero rest mass. So next point, that is 4.5.2, line emission spectrum of hydrogen. When a substance is irradiated with light, it absorbs energy. Atom molecules or ions which have absorbed radiation are said to be excited. When any atoms or molecules which have absorbed radiation are said to be excited. Heating can also result in an excited state. Heating can also result in an excited state. When an excited species give away the absorbed energy in the form of radiation, the process is called emission of radiation. The recorded spectrum of this emitted radiation is called emission spectrum of all the elements. Here, simple example, hydrogen has the simplest emission spectrum. When electric discharge is passed through gaseous hydrogen, it emits radiation. Hydrogen emission spectrum was studied by 5 scientists in late 19th century. They recorded the hydrogen emission spectra in different regions of electromagnetic radiation. The spectra were not continuous and compared to a series of lines corresponding to different frequencies as shown in figure. In your textbook, the 0.5, 3, 3.5 to 2.5, that type of reading is given. This image I have to introduce from online. So simple, but the values will be changed, but the theme of diagram is same. So simple, first open 0 to 300, it is Lyman, which part is ultraviolet. Second part, that is Balmer series, that is partly visible in visible region. And next one, Pascal series will be present in IR. Also Pfon also present in IR. That type of simple diagram you have to observe. So next, that is line emission spectrum of hydrogen, continues you have to discuss here. In the year of 1885, Balmer expressed the wave number of the emission line in the visible region of electromagnetic radiation by the formula, that is nu bar is equal to 109677 in bracket 1 upon 2 square minus 1 upon n square centimeter, where n is equal to 3, 4, 5, 6, 7 dash. So the line described by the formula are called Balmer series. After this, J. Rydberg found that all the 5 series of line could be described by the following general expression, that is nu is equal to 109677 in bracket 1 upon n square minus 1 upon n2 square, brackets complete, that cm minus 1, where n is the constant, that is n1 is constant, then what the n1 is value is equal to 1, 2, 3, 4, 5 dash. Then n2 is equal to different value, that is n1 plus 1, n1 means simple n1 is the constant, then n1 plus 1, n1 plus 2, n1 plus 3 dash dash. Okay, the above values 109677 cm is called Rayburg constant for hydrogen, that is RH. The table 4.5 shows the distinct feature of these 5 series. Simple next, the table will be show here. This series of emission spectral line for hydrogen. First series Lyman, Balmer, Pascan, Brackett and Pfund. Here simply you have to memorize N1 value is constant, where N2 is equal to N1 plus N2, N1 plus 1, 2, 3, 4, 5. Suppose Lyman's N1 is equal to 1, then N2 is equal to 2, 3, 4 and 5. Which part is present in ultraviolet region? Balmer N1 is equal to 2, then what the value will be starting from 3, 4, 5. N1 is equal to 2, then values will be starting from 3, 4, 5. When Pascal series N1 is equal to 3, then values will be starting from 4, 5, 6, 7. Bracket N1 is equal to 4, then values will be start N2 is equal to 5, 6, 7, 8. So Pfund N1 is equal to 5, then values will be starting from 6, 7, 8, 9, 10, so on. These all are present in what the spectral region is equal to. First is ultraviolet, second is visible, third one is IR, next one also IR, and last also IR. Okay, next one. Simple to solve problem is discussing here. First problem 4.4. What is the visible light has wavelength regions from 400 nanometer to 750 nanometer. 400 is equal to violet and 750 is equal to red. Express these wavelength in the terms of frequency. Simply you have to give one, that is 1 nanometer is equal to 10 raised to minus 9 meter. Simple solution is there. We know that what the relation between C is equal to nu into lambda. Therefore, when you have to calculate nu, then that is nu is equal to C upon lambda. Therefore, frequency of violet light is equal to, simply you have to calculate what is the speed of light value is, we know that is 3 into 10 raised to 8 meter per second. That is common for all spectral light. So 3 into 10 raised to 8 upon what is the violet value is equal to 400 into 10 raised to minus 9. It gives what is the value is equal to 7.50 into 10 raised to 14 hertz. This first value, second value, and simply you have to calculate. And frequency of red light, that is equal to also 3 into 10 raised to 8 meter per second upon 750 into 10 raised to minus 9. Simple answer, that is equal to 4.00 into 10 raised to 14 hertz. Okay, then next problem. Problem number 5, that is near same as last last problem. Parameter of blue and red region, that is 400 nanometer and 750 nanometer, we know that is respectively. which of these two is higher? दोनों में से आपको हायर एनर्जी किसका है वो फाइंड आउट करना है. लास्ट टाइम हम लोगों ने दोनों का वैल्यू फाइंड आउट किया. तो सिंपल, what is the solution? 400 nanometer and 750 nanometer are the wavelength of blue and red light. We know that is okay. Then Energy of radiation is given by the expression H is equal to h nu, and nu is the frequency of radiation is related to the wavelength by expression lambda is nu is equal to c upon lambda. Therefore, shorter the wavelength lambda, larger the frequency and higher is the energy. Thus, blue light which has shorter lambda, that is 400 nanometer, than red light, that is 750 nanometer, has a